Hello, today I'm going to attempt to increase the performance of my FeelTech FY3224S function generator. I bought this in 2016 for about £45 from Amazon, and I saw a video a few days ago by TI THS3092 in which he swapped out the final stage op amps, and so I thought I'd have a go doing something similar myself. Now the device that he was demonstrating is similar to this one, but not exactly the same. The model he has is the FY3224S. However, this FeelTech unit does suffer from some of the same issues. So we'll have a look at what those issues are and see if we can fix them. Firstly though, let me show you what the problem actually is. I currently have my signal generator set to 10 MHz with an amplitude of 10 volts or 10 volts peak to peak. We can see these details down here. So you've got 10 MHz and 10 volts peak to peak. You can see that the sine wave is nice and clean. Looks like a sine wave should. But let's see what happens if we start to increase the frequency. So it's still a sine wave at this point. We're up to 13 MHz, 14. You can already see the sine wave starting to look a little bit deformed there. 15, 16, 17, 18. If we go all the way up to this unit's maximum frequency of 24 MHz, you can see that the sine wave at this point is looking more like a triangle wave. The other thing to notice is that the peak-to-peak voltage has dropped considerably from 10 volts down to just over 7 volts, and I haven't changed that setting on the signal generator at all, so it should still be set to 10 volts. Problem stays the same if I increase the peak-to-peak voltage on the signal generator now. It's currently set to 10 volts. If I set it to 11, 12, that's 15 volts, all the way up to its maximum of 20 volts. You can see that not only do we now have a slight DC offset, but the peak-to-peak voltage is still only 8.8 volts. So let's take this function generator apart. Let's have a look at the op amps that are in there, and let's see if we can swap them over. Taken the function generator apart, and this is the synthesizer board. The case is more or less empty, the rest of it seems to just be a power supply. And the two parts that we're interested in are these two op amps here, one there and one there. So looking at the part numbers on these two op amps, the part number is 30021 3VT VPM3, and it does have a Texas Instruments logo on there. However, if you search Google for this part number, I've drawn basically a blank. In fact, the only reference I can find to it is somebody else asking the same question to TI support, and they say that they can't find any record of that marking and package combination, so it looks like it's probably a fake part or a rebadged part or something along those lines. So what we're going to do is replace the op amp there with one of these, and this is a genuine TI part. This is a THS3092, and we're going to see if that makes any difference to the output at high frequencies. I've now changed the op amp on channel 1, but not on channel 2 on the function generator. So we're looking at channel 2 at the moment on the scope, and it's currently set to 10 MHz and 10 volts peak to peak. So this is the unmodified channel. If I start to turn up the frequency here, we can see that it's fine at 13, 14, 15. We've still got 10 volts peak to peak, which is good. 16, 17. You can see it now starts to drop. It gets 18. 19, we see the disfiguration of the wave, and by the time we get up to 23 megahertz, we've actually dropped down to 7.5 volts. We go to 24 if you like, and we've got down to about 6.8 volts at that point. Let's go back to 10 megahertz again, and let's switch over to channel 1. Now this is the one I've changed. This is the one where I've swapped out the op amp for the new one. So here we are again at 10 MHz. Let's start increasing the frequency. So you can see we're still getting a little bit of distortion in the shape there, but we're now at 23 MHz there, and we've still got 10 volts peak to peak. So I'd say that was reasonably successful. You can now see both of the op amps soldered onto the board. They were quite easy to solder on, but they were a little bit trickier to remove. I don't have a hot air rework station, unfortunately, so I ended up using a slightly more ghetto version, which is this paint stripper gun just here. I don't recommend anybody actually try this. You can see that when I did, I slightly melted the buzzer up here. I did protect the caps by wrapping them in foil and Kapton tape before I started doing this, but in general it's not a very good idea. What remains to be done is to put this all back into its enclosure again. Don't forget to replace the heatsink. You can see the little screw hole for it just there. I'm going to add some thermal paste to it as well, just to help that along a little bit. So let's put it all back together and see if it still works. Let's just check that everything's working then. The op amps on both channels have now been replaced. We're looking at a 10 MHz sine wave here, 10 volts peak to peak. If I start to increase this, got 16 megahertz, 17, 20 megahertz, 21, 22, 23, 24, and we're still holding that 10 volts peak to peak. Alternatively, if we go down a little bit, back to 10 megahertz again, we can also change the amplitude here. So we're on 10 volts at the moment. Let's go up a little bit to 11, 12, 13, 14, 15, 16. It's basically keeping pace. Go all the way up to its maximum, which is 20. And we can see there in the bottom left hand corner we're getting 19.6 or 19.8 volts peak to peak, which is pretty decent. So overall, reasonably successful. Do I think everybody should do this? Not necessarily. Those particular op amps are reasonably expensive. I think they were about £4 each, something along those lines. And this was more of something to do because I thought it might be interesting, rather than because it'd be massively useful. I very rarely need sine waves at 25 megahertz anyway. Okay, that's all for now. Thanks very much. See you next time.